Suppose we have a set of finite vectors B. So we have A1, A2, up to the vector AN. And this finite set of vectors is in any vector space V. And B is a linearly independent set. And the set B also spans the vector space V. Then B is called a basis for the vector space V. So note that basis vectors aren't necessarily orthogonal unit vectors. So they need to be linearly independent and span V, such that all vectors in the vector space can be expressed as a linear combination of these vectors. And basically, they identify a direction and spacing. And the basis vectors can have different units in different directions. So for example, x can refer to space and y can refer to time. So having the same units and spacing in both directions is important in geometry, but not other applications like physics, where different physical quantities are used. Now let's look at a few examples. So suppose we have a set of finite vectors being the unit vectors in 3 space. Well, as we've shown previously, set B is a linearly independent set. So these unit vectors cannot be expressed as a linear combination of the other unit vectors. And B spans the vector space R3. So therefore B is a basis for V, as it satisfies these conditions. So any vector in 3 space can be expressed as a linear combination of these basis vectors. So in this special case, these vectors form a standard basis for R3. Now suppose we have the set of vectors being 1, x, x squared, up to x to the power of n, in the vector space of polynomials with a degree less than or equal to n. So recall that we can treat these as vectors with one component, and we've shown previously that B forms a linearly independent set. Because recall that the coefficients multiplied by these vectors sum together, so we have C0 plus C1x plus C2x squared, and so on up to Cn by x to the n is equal to 0 only if these coefficients are all 0, which is the trivial solution. Noting that x has an arbitrary value in the interval from -infinity to infinity. And recall that any polynomial with a degree less than or equal to n can be expressed as the linear combination of these polynomials. So therefore, the span of B is the vector space Pn. So effectively B spans this entire vector space. So any polynomial with a degree less than or equal to n can be expressed as a linear combination of these polynomials. So therefore, B is a standard basis for Pn. And let's do one more example where we have B being a set of matrices M1, M2, M3 and M4. So M1 has an entry of 1 in the first row and first column, and 0s otherwise. And similarly, M2 has a 1 in column 2 and 0 otherwise. And M3 has a 1 in row 2 column 1 and 0s otherwise. And M4 has a non-zero entry in row 2 on column 2. And we want to see if this set of matrices forms a basis for the vector space of 2 by 2 matrices. So to show this, we test for linear independence. So we have a coefficient C1 by M1 plus C2 M2 plus C3 M3 plus C4 M4. And we set that equal to 0. So therefore this equation only has the trivial solution, because we have C1 by 1 plus 0 by C2 is 0 plus 0 by C3 plus 0 by C4 is equal to 0. So therefore C1 is equal to 0. And by a similar argument, C2 is equal to 0 and C3 is 0 and C4 is also equal to 0. So therefore B is a linearly independent set. And now we want to verify if B spans its vector space. So therefore we set this equation equal to some arbitrary matrix, so that has arbitrary values of B11, B12, B21 and B22. So now this equation has a solution where C1 is equal to B11, C2 is equal to B12, C3 is equal to B21 and C4 is equal to B22. So given these entries are arbitrary, then B spans its vector space of 2 by 2 matrices. So given these two conditions are satisfied, then B is a standard basis for the vector space of 2 by 2 matrices. Some vector spaces have no basis because they don't have a finite spanning set. And an example is R infinity. So suppose we have a finite spanning set of vectors with an infinite number of components, being 1, 0, 0, and so on with all zeros. And then we have 0, 1, 0, with the rest of the components being 0, and 0, 0, 1, with the rest of the components being zeros, and so on. up to some vector that has all 0 components and a single component of 1. And this has to be a finite spanning set. So we have a finite number of vectors. And therefore this finite set of vectors in R infinity cannot be used to represent every vector in this vector space. So therefore this vector space has no basis, because that is a finite spanning set, which can't represent a vector with infinitely many components. And another example is a vector space of polynomials with an infinite number of terms. And suppose we have a finite set of vectors being P0, P1, P2, and so on, up to Pn. So given we have a finite number of polynomials, any polynomial with a degree less than or equal to n can be written as a linear combination of these polynomials. And therefore this vector space has no basis. If a vector space V has a basis, being the finite set of vectors in V, then every vector in V can be expressed in exactly one way, being the linear combination of these basis vectors. So we're up to the scalar Cn by An. And these scalars are called the coordinates of vector A relative to the basis B. So if we can find more than one basis for the given vector space, then we can have different coordinates of A depending on those basis vectors. So we can express this as a coordinate vector relative to the basis B. So that's equal to those coefficients of the linear combination of the basis vectors. So for example, in 3 space, we can visualize this vector as having some x coordinate, some y coordinate, and some z coordinate. So we can write this vector as a linear combination of the basis vectors. And therefore the coordinates of A relative to the standard basis, being the finite set of unit vectors, are x, y, z, which are the coefficients of this linear combination. Let's determine if the following vectors form a basis for R2. So we have some constant by the first vector plus some constant by the other vector is equal to the 0 vector. So we first test for linear independence. So that gives a system of linear equations. So we have C1 plus 3C2 is equal to 0, and 2C1 plus C2 is equal to 0. And therefore our matrix of coefficients is 1, 3, 2, 1. And if we take the determinant of this matrix, we get 1 by 1 minus 3 by 2, which is minus 5. And given that the determinant is non-zero, then this system of equations only has one trivial solution, being C1 is equal to 0 and C2 is equal to 0. So therefore the set of these vectors is a linearly independent set. And now we must test if this finite set of vectors spans this vector space. So to do that, we set the right hand side of this equation to some arbitrary vector. So we have b1, b2 being the components of that vector. So again, given the determinant is not 0, then the inverse exists. So our solution vector can be written in the form of the inverse of this matrix by the vector b. So therefore this system of equations is satisfied for an arbitrary vector b, and therefore b spans R2. So given these two conditions are satisfied, then the finite set of these vectors is a basis for R2. Given that we found in a previous problem that the finite set containing these vectors form a basis for R2, we're asked to find the coordinate vector of this vector with the following components relative to this basis. So therefore this vector with components 4 and minus 5 is equal to some coordinate, being the coefficient, multiplied by the first basis vector plus the other coordinate by the second basis vector. So on the left hand side we have C1 plus 3C2 is equal to 4 on the right hand side, and then 2C1 plus C2 is equal to minus 5. So therefore this is a non-homogeneous linear system that can be solved by taking the inverse of the coefficient matrix and multiplying by the vector on the right hand side. So therefore we can write this as C1 C2 is equal to the inverse of the coefficient matrix by the vector with the following components. So I'll leave it for you to find the inverse, and you'll obtain C1 is minus 3.8 and C2 is 2.6. So therefore we can write the coordinate vector relative to the basis, being the finite set of these vectors, is equal to minus 3.8 and 2.6. And then we're asked to find the vector that has the following coordinate vector relative to this basis. Well, what we do is write the vector as a linear combination of the basis vectors using the components of the coordinate vector. So what we have is 3 by the first basis vector minus 2 by the second basis vector. So for the first component, we get 3 minus 6 is negative 3. And then we have 3 by 2 is 6, minus 2 by 1, which is 4.